So we have seen that energy is conserved when the Lagrangian doesn't depend explicitly on time. What about mass? We have said nothing about mass conservation. We have been told for years that mass is conserved, in particular in chemical reactions, but in fact it's a lie, and I will show you that indeed mass is usually not conserved. So to show that, we'll consider an atomic nucleus decaying by emission of a gamma ray. So initially we have a nucleus of mass m0, and we consider its rest frame, so its proper frame in which it is not moving. Therefore its energy is just E0 equal m0 c squared, and its momentum p0 is 0. After the emission of the photon is carrying an energy E gamma and a momentum p gamma. And of course, the mass of the photon, m gamma, is 0. So we have a relationship between the energy of the photon and its momentum, which is simply E gamma equal p gamma times c, the speed of light. And for the nucleus, after the decay, we will write its energy E1 and its momentum P1. And also, we will not assume that its mass is the same as before the decay, so we will write it M1. Applying energy conservation, we have E0 equal to E1 plus E gamma. And applying momentum conservation, we have P0 equal P1 plus P gamma. But because P0 is equal to 0, we have P1 plus P gamma equal to 0, so P1 equal minus P gamma, and in magnitude these two vectors have the same value, so P1 is equal to P gamma. Now for the energy, we have E0 equal m0 c squared, and E1 is equal to square root of m1 squared c4 plus p1 squared c squared. And we have the energy of the gamma, which is just p gamma times c. So using the energy conservation equation, we finally get a relationship between the masses and the momenta, where we have used the fact that P1 is equal to P gamma. Now we solve for M1. So we see that M1 and M0 cannot be the same masses. Even if we consider the energy of the photon to be much smaller than the energy the mass energy of the atom is 0. We get an equation using a Taylor expansion, which gives M1 approximately equal to M0 times 1 minus E gamma on E0. And replacing E0 by M0 c squared, we see that the difference of mass is just the energy of the photon divided by c squared. And the energy of the photon cannot be 0, because a photon with 0 energy is simply no photon at all. We took the example of an atomic nucleus here, but this is true for any system which will emit a photon, a molecule, an atom, a nucleus, a particle. Whenever a photon is emitted, the mass of the system is changed. There is no choice. Some particles, like elementary particles, like the electron, for instance, have a well-defined mass, and they can't change their mass. Therefore, an electron will never be able to emit a photon by itself. It will always have to interact and exchange energy with another system in order to do so. and that's because the electron has the same mass in all inertial frame.